The wind held a different kind of bite on the northern Great Plains, a truth Thomas Brennan learned harshly in his first winter of 1874. His wood stove, a ravenous beast, devoured cord after cord of wood, yet ice still crept across his cabin floor, mere steps from the roaring fire. He had meticulously constructed his homestead according to the widely accepted standards preached to every settler from Iowa to the Dakotas: thick log walls, a centrally located iron stove, all Army manual approved and considered foolproof. Yet by February, he burned through what should have been a 3-family wood supply, and the cold relentlessly seeped into every nook and cranny. Across the vast territory, homesteaders were engaged in the same frustrating and losing battle, their cabins built, by the book, but failing miserably against the unforgiving freeze. Quietly, Brennan began to innovate. He dug trenches beneath his floorboards, ingeniously rerouting heat using methods borrowed from the Plains tribes. His neighbors, initially skeptical, mocked this trench system as wasteful excess. But when the next brutal winter descended, Brennan's cabin remained a comfortable 45 degrees warmer, all while consuming 30% less wood. What understanding of subterranean heat transfer did he possess that eluded every experienced builder? Disaster struck Jacob Mueller's cabin, a mere 3 miles east, on a Tuesday night in late January. The mercury plunged to a staggering 28 degrees below zero and stubbornly remained there for 4 consecutive days. Mueller, too, had faithfully followed every recommendation in the territorial handbook: a cast-iron Acme stove positioned precisely in the center, a 6-inch stovepipe ascending directly through a reinforced roof collar, and seasoned oak split to the regulation thickness. By the second morning, his youngest daughter, Mary, pointed out that her breath was visible inside the cabin. By the third night, Mueller discovered delicate ice crystals forming around the doorframe, despite the fire blazing hot enough to make the stove glow a menacing red. Thomas Brennan arrived on horseback Thursday morning to find Mueller's family huddled together on the sleeping platform nearest the stove. The children's fingers bore the unmistakable white patches of mild frostbite. The thermometer on Mueller's far wall registered a chilling 14 degrees Fahrenheit. The stove-devoured split would faster than Mueller could feed it, yet the precious heat seemed to vanish into the cabin's corners and ceiling, leaving the floor so frigid that standing barefoot for even 30 seconds became an unbearable ordeal. Mueller had done everything right, adhering strictly to conventional wisdom. His cabin measured 16 by 20 feet with 8-foot ceilings, precisely the dimensions recommended for efficient heating. The logs were meticulously chinked tight with clay and moss. The foundation stones were laid level and mortared solid. The door fit snugly in its frame, yet the heat stubbornly rose straight to the ceiling, lingering there uselessly, while the living space remained bitterly cold. Brennan had witnessed this disheartening pattern before, during his 12 years trading throughout Minnesota and the Dakotas. Every trading post, every settler cabin, every military outpost suffered from the same fundamental flaw. Conventional stoves heated air, and hot air, as nature dictated, rose. The moment that heated air reached the ceiling, it became trapped above head level, creating a layer of warmth that benefited no one. Meanwhile, the floor remained as cold as the frozen ground beneath it, and frigid air crept in from every corner where families actually lived and slept. The Army Manual, which served as the Bible for most frontier construction, naively assumed that hot air would somehow circulate naturally throughout a cabin. But Brennan had learned, through hard experience, that this simply never happened. Heat moved upward and stayed there. The floor, where children played and families gathered, remained the coldest part of any cabin built by standard methods. 3 winters prior, while trading along the Missouri River, Brennan had spent February recuperating from a broken leg in a Mandan village. The tribal heating system had fascinated him. Instead of simply burning wood in a central fire pit and hoping the heat would somehow spread, the Mandan meticulously directed smoke from their fires through carefully constructed channels that ran beneath raised sleeping platforms. The smoke traveled horizontally through these earthen tunnels before exiting through wall openings. The heated earth beneath the platforms radiated warmth upward for hours after the fires had died down. An elderly Mandan builder named Running Wolf explained that this technique had been passed down from Eastern tribes, who in turn had learned it from Korean traders generations ago. The Korean ondol system used the same underlying principle. Instead of heating air directly, heat the ground beneath your feet, and the warmth will naturally rise into your living space. Running Wolf had ingeniously adapted this ancient method using local materials and the constraints of the frontier, creating heated floors that kept families warm throughout the brutal plains winters. Brennan realized that Mueller's problem, and indeed the problem facing every frontier family, wasn't about burning more wood or building thicker walls. The core issue was where the heat went after it left the stove. Conventional wisdom sent all that precious heat straight up to the ceiling, where it did absolutely no good. But if he could redirect that heat horizontally through channels beneath the floor, in the manner Running Wolf had demonstrated, the heat would warm the earth under the cabin and radiate upward into the living space. The solution, Brennan understood, required thinking about heat as something that could be moved and stored, not just created. Instead of allowing hot air and smoke to escape immediately through the chimney, Brennan would capture that heat and force it to travel a longer path through underground channels before allowing it to exit. The earth and stone in those channels would absorb the heat and release it slowly, effectively turning the entire floor into a massive, radiating heating surface. Brennan began sketching plans that very evening. His system would require digging trenches beneath the cabin floor in a zigzag pattern, lining those trenches with flat stones, and sealing them with clay to create airtight channels. The stove would connect to these underground passages, forcing all smoke and heat to travel through the entire network before exiting through a chimney positioned at the far end of the cabin. When Brennan described his plan to Mueller and the other neighbors who gathered to discuss the heating crisis, their reactions ranged from deep skepticism to outright ridicule. Wilhelm Grass, who had constructed 4 cabins using Army manual specifications, dismissed the trench system as Indian nonsense that would collapse the floor and fill the cabin with smoke. Sarah Henderson, whose family had endured 3 Dakota winters using conventional stoves, declared that digging holes under a perfectly good cabin was the act of someone who had simply spent too much time alone in the wilderness. Even Mueller, despite his family's current suffering, hesitated to attempt such an unconventional modification. The method required tearing up floorboards, excavating tons of dirt and rock, and completely rebuilding the heating system according to principles that no one in their community had ever tested. If the experiment failed, Mueller would be left with a destroyed cabin and no way to heat his family through the remaining winter months. But Brennan had witnessed too many frontier families suffering through inadequate heating to ignore what he had learned from Running Wolf. The conventional method was not merely inefficient, it was fundamentally flawed in its understanding of how heat moved through enclosed spaces. Brennan began construction on the first Monday in February, when the ground temperature held steady at a frigid 18 degrees Fahrenheit, cold enough to prevent the excavated earth from turning into mud, but not so frozen that digging became impossible. He started by removing 12 floorboards from the center section of his cabin, exposing a rectangular area measuring 8 feet by 14 feet of packed dirt floor. The trench network demanded precise measurements to ensure proper heat distribution. Brennan carefully laid out a pattern of channels that would force heated air to travel the maximum distance before exiting. The main trunk ran lengthwise down the cabin center, measuring 18 inches wide and 14 inches deep. 3 lateral branches extended perpendicularly from this central channel, each branch measuring 12 inches wide and 10 inches deep, creating a pattern that resembled a tree trunk with evenly spaced limbs. Excavating through the frozen earth took 6 days of steady work with pickaxe and spade. Brennan discovered that the soil 18 inches below the surface contained a layer of dense clay mixed with small stones, the perfect material for creating airtight seals. Once the trench system was complete, he carefully separated this clay-rich earth from the regular topsoil, storing it in wooden crates inside the cabin where it would remain workable. The stone selection process proved more challenging than the digging. Brennan needed flat rocks that could be fitted together tightly enough to prevent smoke leakage, while creating smooth passages for airflow. He spent 2 full days at a limestone outcrop 4 miles north, carefully selecting pieces that measured between 6 and 10 inches wide with relatively flat surfaces on both sides. Each stone had to pass a specific test. When placed against another stone, the gap between them could not exceed the thickness of a knife blade. Laying the foundation layer required positioning these limestone pieces to create a continuous channel floor. Brennan discovered that slightly overlapping the stones, like roof shingles, effectively prevented smoke from seeping through the joints. He used the clay-rich soil as mortar, mixing it with water heated over his cook stove until it reached the consistency of thick porridge. This clay mortar had to be applied while still warm to bond properly with the cold stones. The sidewalls of each trench demanded even more precision. Brennan selected stones with one straight edge to form vertical surfaces, stacking them 3 layers high to create channels with consistent interior dimensions. The main trunk measured 11 inches from floor to ceiling after stone installation, while the lateral branches measured 8 inches high. These dimensions were crucial. Too narrow, and the airflow would be restricted. Too wide, and the heat would dissipate before reaching the end of the system. Sealing the channel tops presented the most technically demanding challenge. Brennan cut flat stones into rectangular pieces that spanned each trench width, creating solid caps that could support the weight of floorboards and furniture above. Every joint between capstones received a generous application of clay mortar, followed by a second layer of the clay-rich earth mixed with chopped grass for reinforcement. This double sealing technique ensured that heated air would follow the design path rather than escaping upward through gaps. The connection between stove and trench system required fabricating a custom adapter from sheet metal salvaged from old coffee tins. Brennan hammered these metal pieces into a funnel shape that fit snugly over the existing stovepipe opening, then extended this funnel into the beginning of the main trunk channel. The junction had to be perfectly airtight to prevent smoke from entering the cabin while directing all combustion gases into the underground network. Installation of the exit chimney at the far end of the cabin involved cutting through the log wall and constructing a stone-lined opening that connected to the final lateral branch. This exit point positioned the chimney 8 feet away from the stove, forcing all heated air and smoke to travel through 42 feet of underground channels before escaping to the outside atmosphere. The first test came during a cold snap in early March, when overnight temperatures dropped to a bone-chilling 26 degrees below zero. Brennan loaded his stove with split oak and meticulously monitored the system's performance using a collection of thermometers placed at various points throughout the cabin. Within 2 hours of lighting the fire, the floor temperature above the main trunk measured a comfortable 68 degrees Fahrenheit, while the floor above the lateral branches reached 62 degrees. More significantly, the floor retained substantial heat long after the fire died down. 12 hours after the last piece of wood burned to ash, the floor above the trench system still measured 41 degrees Fahrenheit, warm enough to walk on barefoot comfortably. The conventional stove in his neighbor's cabin, by comparison, left floors that dropped to within 5 degrees of the outside air temperature within 3 hours of the fire dying. Wood consumption measurements revealed the system's remarkable efficiency. Brennan's modified cabin required only 2 armloads of split wood to maintain comfortable interior temperatures for 18 hours, compared to the 6 armloads that Mueller consumed in his conventionally heated cabin during the same period. This represented a 70% reduction in fuel requirements while maintaining significantly higher comfort levels. The thermal storage capacity impressed Brennan the most. The limestone and clay in the underground channels absorbed heat during active burning periods and released it gradually throughout the day and night. The entire floor functioned as a massive heating surface, radiating warmth upward into the living space at a steady rate that eliminated the temperature swings common in cabins with conventional stoves. Temperature readings taken during the coldest night of March showed interior cabin temperatures ranging from 58 degrees to 62 degrees Fahrenheit, while the outside air dropped to 31 degrees below zero, demonstrating the system's ability to maintain livable conditions even during extreme weather events. Word of Brennan's success reached Eric Larson during the spring thaw, when melting snow revealed the stark difference between cabin roofs throughout the settlement. While conventional cabins showed irregular patches of bare wood where escaping heat had melted accumulated snow, Brennan's roof maintained an even layer of white coverage that indicated minimal heat loss through the ceiling structure. Larson, a Norwegian carpenter who had immigrated to the territory 2 years earlier, immediately recognized the significance of this snow pattern. In the forests around Bergen, his grandfather had taught him that a properly insulated building should never melt snow from its roof during winter months. Heat escaping upward through ceiling gaps represented wasted fuel and compromised interior comfort, problems that Scandinavian builders had solved generations ago, using techniques largely unknown to most American frontier construction. Larsen visited Brennan's cabin in late April and discovered that, while the underground heating system had solved the fundamental problem of floor warmth, significant thermal inefficiencies remained in the building envelope. Using a lit candle held near wall joints and ceiling corners, Larsen demonstrated how air currents indicated dozens of small gaps where heated air escaped and cold drafts entered. These infiltration points negated much of the benefit gained from the innovative floor heating system. The Norwegian approach to log cabin insulation involved a double barrier technique that traps still air between layers of natural materials. Larsen showed Brennan how to prepare a chinking compound using clay soil mixed with chopped prairie grass, animal hair collected from buffalo wallows, and dried moss gathered from stream banks. This mixture, when properly proportioned, created an elastic seal that expanded and contracted with the logs without cracking during temperature changes. Application required removing the existing basic mud chinking and widening each gap between logs to create uniform channels measuring 3 inches deep and 2 inches wide. Larsen demonstrated the proper technique for packing the new compound. First, a base layer of clay mixture pressed firmly against the back of the channel, then a middle section filled with loose moss for insulation, and finally a weather-resistant outer layer of clay mixed with pine pitch to shed water. The roof modification presented more complex challenges. Conventional frontier construction used single-layer board roofing covered with split shingles, a method that allowed substantial heat loss through gaps between boards. Larsen's Scandinavian technique involved creating an insulation chamber between the existing roof boards and a new inner ceiling layer constructed from additional planks. This airspace, measuring 4 inches deep across the entire ceiling area, was filled with a mixture of dried grass, pine needles, and small stones that provided thermal mass while preventing air circulation. The inner ceiling boards were sealed with clay mortar at every joint, creating an airtight barrier that prevented warm air from reaching the cold outer roof surface. Installation required constructing a framework of support beams to carry the weight of the new ceiling and insulation materials. Brennan and Larsen spent 5 days cutting and fitting dimensional lumber, creating a grid pattern that divided the ceiling into manageable sections for insulation placement. Each section measured approximately 3 feet square, allowing easy access for filling and future maintenance. The most critical technical innovation involved creating vapor barriers using materials available on the frontier. Larsen had learned that moisture from cooking and breathing could condense within insulation materials, reducing their effectiveness and causing structural problems. His solution used sheets of birch bark harvested in large pieces during early summer and carefully fitted to cover the entire inner ceiling surface before the final board layer was installed. Temperature monitoring during the following winter revealed the dramatic improvement achieved by combining floor heating with comprehensive insulation. While the trench system had previously maintained interior temperatures in the low 50s during extreme cold, the insulated cabin now sustained interior temperatures of 68 degrees to 72 degrees Fahrenheit, even when the outside air dropped to 25 degrees below zero. More significantly, the building now required 40% less wood to maintain these higher temperatures compared to Brennan's original modified system. The combination of radiant floor heating and superior thermal retention created a synergistic effect, where each improvement amplified the benefits of the other. Heat generated by the underground system was now captured and held within the living space instead of escaping through the building envelope. Humidity control became an unexpected additional benefit. The vapor barrier system prevented interior moisture from condensing within wall and ceiling cavities, eliminating the ice buildup and wood rot that plagued conventional frontier cabins. Interior air quality improved noticeably with the elimination of drafts and cold spots that created uncomfortable living conditions in standard construction. The thermal mass principle extended beyond the floor system as Brennan discovered that the clay-rich insulation materials absorbed and released heat throughout daily temperature cycles. During sunny winter days, south-facing walls warmed enough to contribute additional radiant heat to the interior space. At night, This stored thermal energy helped maintain stable temperatures long after the stove fire diminished. Snow accumulation patterns provided visible proof of the system's efficiency. Throughout the brutal winter of 1875 to 1876, Brennan's cabin roof maintained consistent snow coverage, while neighboring structures showed clear evidence of heat loss through bare patches, ice dams, and icicle formation along eaves. Fuel consumption records kept by Brennan documented the combined improvements achieved through integrated thermal design. His cabin used approximately 1 cord of split hardwood per month during the coldest periods, compared to the 2.5 cords consumed by Mueller's conventionally heated cabin of similar size. This represented savings of 18 cords of wood over a typical 6-month heating season. The success attracted attention from other Norwegian and Swedish immigrants who recognized familiar techniques adapted to plains conditions. Word spread through ethnic communities that someone had successfully combined old-world thermal engineering with frontier materials and American innovations. By spring, delegations of immigrant builders visited Brennan's homestead to study the integrated heating and insulation system that had proven itself through 2 severe Great Plains winters. The summer of 1876 brought unprecedented challenges that would test whether Brennan's innovations could protect against threats beyond winter cold. By early June, the territory had received only 3 inches of rainfall compared to the usual 8 inches, and prairie grass stood brown and brittle under the relentless sun. Lightning strikes ignited grass fires that burned for days across the dry landscape, while settlers watched their water sources shrink to muddy pools. Brennan recognized that his efficient heating system meant nothing if wildfire destroyed his cabin or drought forced him to abandon his homestead. The same Plains tribes who had taught him underground heating techniques also possessed sophisticated knowledge about managing fire and water in this harsh environment. Through conversations with a Lakota trader named Joseph Crow Feather, Brennan learned that survival required thinking about his cabin as part of a larger landscape system rather than an isolated structure. Crow Feather explained that prairie fires moved according to predictable patterns determined by wind direction, fuel density, and terrain features. A properly designed fire break could redirect flames around valuable structures, but only if the break was wide enough and positioned to account for wind patterns and ember transport. Most settlers created ineffective fire breaks by simply clearing grass in narrow strips around their buildings, not understanding that burning embers could jump distances of up to 200 yards during strong wind conditions. The Lakota method involved creating multiple defensive zones at different distances from structures. Brennan began by establishing a primary fire break extending 150 yards in all directions from his cabin, removing all combustible vegetation down to bare soil. This zone required burning off existing grass during controlled conditions, then maintaining the cleared area by regular cultivation to prevent regrowth. Within this primary zone, Brennan constructed a secondary defense consisting of strategically placed green belts where fire-resistant plants could grow. He transplanted cottonwood saplings and established patches of broadleaf plants that retained high moisture content even during dry periods. These living fire breaks would not burn readily and could stop low-intensity fires that penetrated the outer defensive zone. The most innovative element involved creating water storage systems that served dual purposes for fire suppression and drought survival. Crow Feather had observed how certain landscape features naturally collected and held rainwater and showed Brennan how to modify the terrain around his cabin to capture every drop of precipitation that fell on his property. Brennan excavated a series of interconnected basins positioned to collect runoff from his cabin roof, the cleared firebreak area, and natural drainage patterns. The largest basin, located 50 yards northeast of the cabin, measured 20 feet long by 12 feet wide by 4 feet deep with sloped sides lined with stones to prevent erosion. This primary reservoir connected through shallow channels to 3 smaller basins positioned at strategic points around the cabin. The collection system required precise grading to ensure water flowed from collection areas into storage basins without creating stagnant pools that would breed mosquitoes or contaminate drinking supplies. Brennan used a simple water level made from a wooden trough filled with water to establish proper slopes for drainage channels, ensuring a gradual descent that moved water efficiently without causing erosion. Roof water collection presented technical challenges that frontier builders typically ignored. Brennan fabricated gutters from split logs hollowed into U-shaped channels, positioning these along the cabin's eaves to capture rainfall and direct it toward the storage system. The gutters required careful installation with slight downward slopes toward collection points and regular maintenance to prevent blockages from leaves and debris. During the July drought, when most settlers were hauling water from sources more than 5 miles away, Brennan's collection system provided adequate supplies for drinking, cooking, and maintaining his fire-resistant plant barriers. The stored water also enabled him to keep surrounding soil moist enough to prevent dust accumulation that could fuel fires approaching his property. The first major test came during a grass fire that started 15 miles southwest of the settlement on a hot afternoon in early August when sustained winds exceeded 25 miles per hour. Brennan watched the smoke plume grow throughout the day, and by evening he could see the orange glow advancing across the prairie toward his homestead. He spent the night using stored water to saturate the ground within his secondary defensive zone, paying particular attention to areas where windblown embers were most likely to land. The fire reached his outer firebreak just before dawn, arriving as a wall of flames nearly 8 feet high, moving at approximately 4 mph across the dry grassland. The primary firebreak performed exactly as designed, forcing the main fire to split and flow around the cleared zone like water around an island. However, burning embers carried by the wind created spot fires within the defensive perimeter that required immediate suppression using water from the storage basins. Brennan discovered that the most effective technique involved using wet burlap sacks to smother small fires before they could spread to larger fuel sources. The secondary green belt proved crucial in stopping several ember-ignited fires that penetrated beyond the outer firebreak. The high moisture content in cottonwood leaves and broadleafed plants prevented these areas from supporting sustained combustion, creating natural fire stops that required no human intervention. By morning, the main fire had passed around Brennan's property. The fire continued northeast towards the river, leaving his cabin and its defensive measures untouched. However, it devastated 3 conventional homesteads that lacked adequate fire breaks. His water storage system proved invaluable, providing ample reserves for actively suppressing the blaze during the critical overnight hours when it posed the greatest threat to his property. The drought persisted through September, with the growing season's total rainfall reaching only 40% of the normal amount. Brennan's water collection and storage system sustained his household needs, enabling him to maintain a small vegetable garden that yielded food, while neighboring settlers struggled with withered crops and dwindling water supplies. Temperature readings taken inside his cabin during the extreme heat revealed another unexpected benefit of the thermal mass principles integrated into his heating system. The limestone and clay materials, which stored heat during the winter months, now absorb excess heat during summer days, releasing it gradually during the cooler nighttime hours. This moderated interior temperatures more effectively than conventional construction methods could. This integrated approach to landscape management, fire prevention, and water conservation established a model that other settlers began to emulate as news of Brennan's success spread throughout the territory during a harsh summer that claimed numerous homesteads due to fire and drought. The blizzard that struck in February 1877 became the definitive benchmark against which all future plains winters would be judged. For 9 consecutive days, temperatures never rose above 30 degrees below zero. Winds sustained at 40 miles per hour whipped snow horizontally across the landscape, creating blinding whiteouts that reduced visibility to almost nothing. The storm system stalled over the territory, creating conditions that would rigorously test every aspect of frontier construction and survival planning. Brennan's cabin faced its ultimate challenge during the 5th night, when temperatures plunged to 37 degrees below zero and remained there for 18 continuous hours. While he maintained his normal routine of stoking the stove twice during the night, his neighbors were engaged in desperate battles to prevent their families from freezing to death, even as they burned every scrap of available fuel. Wilhelm Gross discovered that his conventionally heated cabin couldn't maintain livable temperatures, despite his cast iron stove glowing red-hot from continuous firing. By the 3rd day of extreme cold, ice had formed on the interior walls, even though he was consuming 4 times his normal wood allocation. The structural stress from repeated heating and cooling cycles caused his roof beams to contract and expand, creating gaps in the ceiling that allowed snow to drift directly into the living space. Mueller's cabin suffered a catastrophic failure when the constant thermal stress cracked his central chimney, filling the interior with smoke and forcing his family to abandon their shelter during the storm's peak intensity. They survived only by moving into Brennan's cabin, where they found interior temperatures holding steady at 64 degrees Fahrenheit, while outside conditions remained life-threatening. The most revealing comparison emerged through systematic monitoring that Brennan conducted throughout the crisis. Using thermometers positioned at identical locations in his cabin and Mueller's repaired structure, he documented temperature differentials that completely vindicated his integrated approach. While Mueller's cabin experienced interior temperature swings ranging from 38 to 57 degrees Fahrenheit during each firing cycle, Brennan's system maintained temperatures between 61 and 67 degrees, with minimal variation. Wood consumption data collected during the blizzard provided quantifiable proof of the system's efficiency advantages. Brennan's cabin required only 12 pieces of split oak every 24 hours to maintain comfortable conditions, while Mueller consumed 38 pieces in his conventional setup and still failed to achieve adequate warmth. This represented a 68% reduction in fuel requirements while delivering superior comfort and safety margins. The thermal stability proved crucial for more than just comfort. Brennan observed that consistent interior temperatures prevented the condensation and ice formation that plagued other cabins, eliminating structural damage from freeze-thaw cycles that weakened log joints and created air leaks. His systematic approach to moisture control, thermal mass management, and air sealing had created a building envelope that remained structurally sound under extreme conditions. During the storm's aftermath, delegations of settlers began visiting Brennan's homestead to study his methods firsthand. Swedish carpenter Niels Andersson arrived with detailed sketches and measurement tools, documenting the trench system dimensions and connection details for replication in his own construction projects. Norwegian immigrants from the Red River settlement sent representatives to evaluate techniques that reminded them of old-world methods they had thought impossible to recreate on the American frontier. Brennan recognized that successful knowledge transfer required more than casual observation. He developed a systematic teaching approach that broke his integrated system into discrete components that could be understood and replicated by builders with varying skill levels. The documentation process began with creating scaled drawings that showed trench layouts, stone placement patterns, and chimney positioning for cabins of different sizes. This standardization effort revealed technical principles that could be adapted to various frontier conditions. Brennan calculated that his basic trench heating system could be scaled proportionally for cabins ranging from 12 by 16 feet up to 20 by 30 feet, with channel dimensions and layout patterns adjusted according to mathematical ratios he had developed through experimentation. Teaching sessions conducted throughout the spring of 1877 attracted builders from settlements within a 50-mile radius. Brennan discovered that successful knowledge transfer required hands-on demonstrations combined with a systematic explanation of the underlying principles. Students needed to understand not just how to dig trenches and position stones, but why specific dimensions and layouts produced optimal heat distribution. The most challenging aspect involved conveying the integrated nature of the system, where heating, insulation, fire protection, and water management worked together synergistically. Brennan developed a curriculum that taught these elements in a logical sequence, beginning with basic thermal principles and progressing through increasingly sophisticated applications of the underlying concepts. Economic calculations conducted by early adopters provided compelling evidence for widespread implementation. Families who installed complete systems during the summer of 1877 documented fuel savings that averaged 55% compared to conventional heating methods. These savings translated directly into reduced labor requirements for wood cutting and hauling, freeing up time for other productive activities during critical seasonal periods. The success stories multiplied rapidly as word spread through immigrant communities where old-world knowledge validated Brennan's innovations. Letters written by satisfied adopters reached relatives in Minnesota, Wisconsin, and Iowa, creating a demand for instruction that exceeded Brennan's ability to provide personal consultation. By 1878, Modified versions of Brennan's techniques appeared in construction throughout the Northern Plains territories. Each installation demonstrated adaptation suited to local materials and conditions, proving the flexibility and broad applicability of the underlying thermal management principles. The territorial government took notice when reports from frontier settlements documented significantly reduced winter mortality and improved agricultural productivity in areas where the new building techniques had been adopted. Officials began incorporating elements of Brennan's methods into recommended practices for homestead construction, marking the transition from innovative experiment to accepted standard practice. Documentation efforts intensified as territorial engineers recognized the strategic value of proven survival techniques for frontier development. Brennan collaborated with government surveyors to create detailed technical drawings and written specifications that could be distributed to future settlers, ensuring that hard-won knowledge would not be lost to future generations. The legacy extended beyond individual cabins as communities discovered that widespread adoption of efficient heating systems reduced overall demand for timber resources, helping preserve local forests while improving living standards across entire settlement areas. Brennan's integration of indigenous knowledge with immigrant techniques had created a sustainable approach to frontier housing that would influence construction practices for generations to come.